You're listening to a Thames Estuary Partnership podcast, celebrating London's famous tidal river. We hope you enjoy it.
Hello, I'm Eve Sanders and I'm the Estuary Edges Officer at the Thames Estuary Partnership. Welcome to our November episode of Talk of the Thames. I hope lockdown 2.0 is treating you all okay. With the nights drawing in and the weather getting colder, we're hoping this episode will bring you some light autumnal relief. Today, we're going to be talking about the Thames dynamics and answering questions such as why is the Thames brown and what drives the tidal cycles. To answer these questions for us, I'm joined by John Baugh, a Technical Director at HR Wallingford. John, welcome and thank you so much for joining me today. So John, you're a Technical Director based at HR Wallingford, which is a not-for-profit research and consultancy company specialising in water-related challenges. So John, what do you do within HR Linford?
Well, yeah, so we have, my job title is Technical Director, which means there are a bunch of people who are kind of trying to be senior and making sure that as a company we're still achieving the aims that we were set up for originally, which are to do the research that the civil engineering and similar organisations want. So back in the 1940s, people like the ICE and other institutes wanted to have a national hydraulics laboratory in the UK. So they really thought there was a need because they had lots of water-related difficulties, be that maritime, estuary, rivers, flooding, water supply, sewage, all that sort of stuff. So they wanted to establish a laboratory, which they did in 1947, something like that, at the site in Wallingford. So our original purpose is to do that sort of research, kind of applied research, not necessarily what you might expect at university, but applied research to answer questions they want. So that's why we still have quite a technical and R&D focus. In the 80s, because the organisation was already doing a reasonable amount of private consultancy allied to its research strand, Mrs. Thatcher saw it as an easy win as an early privatisation. So she went ahead with that and privatised it as a company limited by guarantee. So we don't have shareholders. So any money we do make, we don't distribute out. We reinvest it in either our facilities or in our own internal R&Ds, to achieve our original aims.
What are some of your sort of big achievements that the company is proud of?
Well, the barrier. Barrier is a big deal. And previous to that, load of work done for Maplin Sands, the port, okay. Seaport, airport thing they had in mind then, and which of course never got built. Yeah, Thames Barrier, and then all the stuff for London Gateway Port. So kind of the EIA support work for them. So the effects of that dredge and that reclamation on waves and currents and sediments and all that sort of stuff. Still work for them as environmental advisors. So the most recent one is Thames Tideway Tunnel. So worked on Thames Tideway Tunnel personally since 2009 up to the kind of planning process, really thinking about the effects of the things in the river, so the riverside rather than the tunnel itself or the hydraulics, thinking about the effect of the structures. And since then, we've been working for the people who are building it in the central region.
Amazing.
And helping them with scour and accretion monitoring and interpreting the answer, the results of all that. So keeping an eye on what's going on compared to what we said would go on, and also allowing things that are unexpected, because there's always unexpected things in a place like the Thames, because it's a dynamic system, to then generate plans to modify and mitigate what's going on.
We're going to delve into a lot more detail about the physical properties of the Thames, which is essentially how the Thames works. So John, how does the Thames work?
Well, it's an interesting location in as much as it's got a twice a day tide, so you get 2 high waters and 2 low waters every day, and that's not entirely unique. I mean, lots of places in the world have tides like that, but also there's places that only have one tide, one high water a day. So the reason that it is as it is if we could delve a bit more into the kind of tidal forces, there's the moon and there's the sun and they have a gravitational pull on the water, and that means that it generates something a bit like a very, very long wave. If you imagine a very long wave, and then that propagates around the oceans, into the seas, into the coastal areas, and into estuaries. And as it does that, it changes, as waves would do. As you shine your light into a prism, it changes. So it's a bit like that. And in the case of the Thames, you've got, in effect, two tides coming at it, one coming up the channel and one coming around the North Sea, and they interact. And it means that in the outer estuary, certainly there's some places where the tide is never slack. It's always moving in some direction or other, because there's these two tidal signals interacting. And then eventually the tide gets into the estuary itself. If you think about it as a wave, which is really quite helpful, rather than, it's not like a river where there's a whole lot of water flowing, it's a wave. As the wave comes into the estuary, it enters a converging area. The banks get smaller, then the cross-sectional area reduces, it gets more, the bed level comes up a bit. And so like a wave on the beach, it deforms, and that means that the amplitude of the wave of the tide increases as you go up the Thames by about a couple of meters. So if you think about mean spring tides, which are it's kind of average largish tide, the range is about 4.5 meters at Southend, but that becomes 6.5 meters by the time you get to Tower Pier. So there's a process of amplification due to just the shape, I guess, the shape of the estuary.
Interesting. And that, so as the tide comes in, how does that affect the ecology?
Well, this is kind of the reason why tides are important, although they're really quite slow. It's very rare that anybody sits at the side of the river and watches it go up and down for 12.5 hours. But it sets the kind of background process for the ecology. So, for instance, salt marsh needs some inundation from the tide, but not lots. So there's a threshold water level above which you'll get the right kind of inundation regime number of, I think it's something like 150 inundations a year, and you expect salt marsh. But less than that, you get much more towards the mudflat. So that's one thing in inundation regime, but also the currents are important. So too much current, you can't have any mud settling. So that stops any intertidal areas being able to be formed in places where the currents are too high. So I think those two factors are probably the main ones. Of course, the fact that there is a current going to and fro is taken advantage of by fish, for instance, who will use the flood tide to get them up the estuary to spawn, and often they hide from the ebb tide. So they have a process that they understand what's going on and take advantage of it.
Interesting. So both habitats are very beneficial to wildlife, like you're saying, the sort of reed beds and the more intertidal type habitats, but also the mudflats, they're hugely beneficial for bird species. Is that right? Absolutely.
So there wouldn't be any, if there's no mud, there'd be no worms and biota, so there'd be no birds. That's a simple way of thinking about it. So birds also are well attuned to what goes on the tide, and you see them arriving at the appropriate moment. And some of them will track the edge of the tide just as it emerges, because they are able to judge that there'll be the various biota won't have burrowed and hidden yet. So you see birds following the tide line up and down quite a lot.
And so with an estuary, and this is sort of a bit of revision for me, so feel free to correct me if I'm wrong, which is likely. You have the sort of saltier water coming in at the bottom and the fresh water coming over the top. How does that change throughout the different areas of the estuary? So from, towards the sea up to the more fresh water near Richmond?
Yeah, so really, one thing about the Thames, broadly, it's quite well mixed in the vertical. So you don't really see much stratification, not extreme stratification like you might see in some places. Like I know the Tees is a good example where up there where when the river flows, the surface all just goes out the whole time, and so that's very stratified because of the way it's been modified over the years. But in the Thames, it's quite mostly well mixed. The main process of salinity that's important is the fact that there is a gradient of saltiness, which leads to a gradient of density of water from the upper tideway out to the sea. So what that does is that it modifies the currents as they go out or in. So for instance, the ebb tide will be larger on the surface. So most water comes out towards the surface on the ebb. But on the flood, it comes in much more flat. So the surface of the bed will be similar. And if you kind of average those in time, you end up with a kind of a net in push for sediment. So particularly in, from Gravesend and the more seaward end up to, let's call it the Barrier or somewhere around the Barking area. So all the way through there is a net push up estuary of the near bed sediment. So you've got a push from the river pushing out, a push from the sea of the near bed sediment going in, and in the middle is what they call the mud reaches, which is where the mud all ends up. And whilst it does vary its location a bit in the year due to the changes to the freshwater flow, there's always a maximum in turbidity, which is kind of a techie word for mud.
Yeah. So within that zone, then, is that quite? I get presuming that's more productive then, and therefore you'd find perhaps more birds.
That's an interesting question, actually. I think you would expect. I think that the difficulty is that as you get further into London, many more of the intertidal areas have been reclaimed historically, which means that the area isn't as much as you might expect. So birds, being sensible, go to where there's large areas because they obviously you need a certain amount of area to cover a certain population of birds, so they tend to go. Even bearing in mind other changes in the types of biota which would be expected for different types of salinity, they need a certain amount of area. So I think though you do see them everywhere, actually. I'm sure anywhere you go, even up into the up to Thames, you still see birds on the intertidals poking away and finding things. And there are some birds, of course, that quite like gravelly beds and look for things underneath there. But in terms of mud, the actual area available is quite important, which drives them further seawards.
Yeah. So that's really interesting. But is any of that unique to the Thames, or is that generic for estuaries? The Thames is obviously quite a heavily modified estuary. So has that had any effects? Does that make it unique in any way?
Well, I mean, in a broad sense, it's almost a generic estuary in terms of being a converging channel, like a trumpet shape. That's kind of, if you went to your Oceanography 101 on estuaries and they said an estuary is a bit like this, they would probably draw something a bit like a trumpet, which looks a bit like the Thames in a broad sense. So whilst it's not unique kind of in that sense, and its tide isn't particularly huge, it's not the 10, 15 meters in the Mersey and the 7 even. 7's 15, isn't it? It's still quite big, and as you say, it's been modified a lot by human intervention because of the location of the city of London, and all the thousands of years, as I was hearing from the archaeology podcast, and all the years that people have always wanted to modify or make use of the river.
Yeah.
So that's meant that it is a combination of a reasonably large tide and a major city is quite unusual. And the other thing about it is that it's there is as you say, a history of modification. So it has been constrained through the ages and dredged over the last, well, probably most significantly over the last 100 years or so, where the channel's been successively dredged, which has meant that the tide has got a bit bigger further up.
So going back to the Thames Barrier with HR Wallingford's involvement, the Thames Barrier is a very iconic structure on the Thames. I think maybe a lot of people think about it if they turn their minds to the Thames. What would cause the barrier to close?
So originally, the design was based around trying to rescue London or protect London from a tidal surge, from a surge. So a surge is where a low water, well, it's the classical version of a surge, a low pressure system moves over the North Sea. So low pressure, so the water goes up to meet the pressure. So there's like a bulge of water somewhere up the North Sea, which then it propagates like a tide would propagate. It goes south, this bulge, and as it comes into the southern North Sea, into the Thames estuary, the size of that bulge increases, and as that combines with the incoming tide, that's how you get a surge tide, and produces an unusual or over large high water level, which would overspill the flood defence, which is what happened in 1953, which is of course the thing that pushed towards the eventual Thames Barrier construction. So the initial thought was about excluding those sorts of surge events, but I think a little bit like whenever you buy something, oh, I could use it for this, but then you realize, I could use it for that as well. And so they got to thinking about it and realized actually they've got an opportunity to manage river flooding also. So you can close the barrier at low water, and you've got a very, very large basin, as it were, from there up to Teddington, which can receive water from the River Thames. So you can use it to evacuate the River Thames to control water in. Presently, they have a matrix of river flow against maximum water level. So there's other models being run in a real-time system, which are doing regular forecasting on those two parameters. And then those numbers go into the guys at the barrier, and they decide whether or not to close it. So sometimes you see it closed for a surge event. Sometimes you see it closed when there's not so much of a surge, but there's a reasonable amount of river flow. So they're trying to manage those two factors at the same time. And I think one thing that the TE 2100 plan, which I think you've already had a podcast about, one thing that did was it thought again about how the balance of those two factors needs to be taken into the plan. So taken into the closure of the barrier, because they were realizing they were getting more and more big flood events from the river, and that was using the barrier more than they would have expected. So they have to modify their thinking about that, and that's how they've revised the plan.
The needs are going to change, aren't they? With climate change, become more intense. So I believe they're considering redesigning the Thames Barrier for it to be able to cope with the demands that climate change are going to bring.
Yeah, that's right. So they've so the plan is kind of a step. Don't do too much first thing. See what's going on, and then respond to that as you go. So the early things you can do, of course, is to improve all the flood defence line as is, and they've done a massive review of all the flood walls and all the assets they've got. There's loads of other flood barriers, of course, on the Thames and related areas, so that the Thames Barrier itself isn't the only thing to concern itself with. So they've done a big review and improved where they need to. And then I believe there's a plan, or there is things you can do to get more life out of the Thames Barrier. You can change the way it operates a bit, and you can modify it a bit to give you more time on the existing structure before you start thinking about anything more major in the future. So trying to get as much value as you possibly can out of this barrier. So originally its life was meant to, I think originally the plan was something like 50-year, but now they realize they can extend its life by being more careful about how they use it and operating it slightly differently to get more to respond to rising mean sea levels and the consequences of that on surge levels.
Interesting. Not forgetting the other flood defences around London. I think it's some mad statistic, like 70% of the Thames is sort of surrounded by concrete, and there's a real push to change that and to sort of rewild the flood defences.
Our friends at the Environment Agency, obviously they're most responsible for defending against floods, so that's their thing, but also they're an environment agency, so they have to concern themselves about improving the environment in general. And I think just the pleasure of walking along the river is quite a thing, and we wouldn't want to ever lose that. And we do need to make space for nature somehow, because as the mean sea level rises, the low water will rise with it, possibly, and that'll mean you'll lose bits of the intertidal, the bottom bit of the intertidal. And furthermore, if there's not enough sediment available to keep the intertidals accreting to keep up with sea level rise, then you'll lose even more. So there is an overall habitat loss if left to itself. And I think the TU200 plan also includes habitat creation in it to try and compensate for that. There's this thing called coastal squeeze, where if it was left to itself, the salt marshes and mudflats would go back, and they would keep up with the sediment, and they would accrete, and they would slowly go back and back into the land. But because we put a wall somewhere, we're saying thus far and no further. So therefore, we have to kind of create or manage our habitat in a different way, whilst also making sure that we don't get wet.
Yes, definitely. So yeah, I think that the Thames was once quite a wide natural floodplain in itself. And I guess over the years, as we've sort of colonised around the Thames, it's been important to almost block the water. I once read a paper that this increases the water flow. It makes, essentially speeds the water flow up.
Well, I think, as I kind of said earlier on, the convergence of a channel makes the tide get bigger. Say you pushed up the walls of the whole Thames forwards a lot, you'd expect a bigger tide. That's what the equations would tell you. And if you then did the opposite, if you could, you'd get a smaller tide. I mean, that's why probably back in olden days, back in archaeology days, that they would have had a wide, shallow, marshy type of estuary, and it would have been very different to what we have now, certainly. And so there's two things that have made the tide bigger. That there have been historical encroachments, so they've gobbled up bits of intertidal, increased the way that the convergence, and also the dredging that has occurred over this century has meant that low water's gone down a bit, which means the tide's a bit bigger, which means the currents are a bit bigger.
So I think a lot of the public view the Thames as dirty because it is visibly brown, and we may have the Kinks to thank for that sort of notion, but why is the Thames brown? Because it's not just pollution, is it?
No, there's a whole lot of just good old sediment, good old lovely, that ecology loves sediment moving around all the time. So I have some numbers somewhere which are kind of, there's thousands of tons moving around in any given tide. So for instance, say for spring tide find some numbers here, okay, right, so say at Gravesend or somewhere like that, there's a good example. There's about 4,500 kilograms passing a place at Gravesend every second during the spring tide. So there's a whole load of mud, and that drops down to about 1,000 kilograms per second maximum passing at say Tower Bridge, somewhere like that. So there's a load of sediment moving around, and that's perfectly natural, and in fact it's vital. So historically, a proportion of the should we call it sediment, would have been sourced from sewage, so particularly from the various combined sewer outfalls that there are. But because of improvements in treatment works, that's improving matters. And also, of course, we've now got the Thames Tidal Tunnel, which is intercepting a load of those combined sewer outfalls. So the amount of sediment that isn't mud is going to be reducing, and has been reducing over the last many years. So the reason that it looks muddy, dirty, because it is dirt. It's actual dirt from a variety of sources, many just coming down from the River Thames. The River Thames itself has got a catchment which accumulates soil and earth from there, and it comes over Teddington into the tidal river. So we shouldn't be afraid of the sediment. It's good.
It's such an interesting concept because, I think that's one of the main things that the Thames sort of struggles with in a way, is that people look at it and think, oh, it's brown, it must be dirty. But the fact is it's naturally dirty. It's meant to look like that. It's an estuary.
It's clean dirt.
It's clean dirt. It's good, clean dirt.
Well, clearly there are areas where, just from historical industrial work, some of the mud is contaminated with various chemicals just because of what was done there in history. So just an idea of how much mud, about 170,000 tons of mud comes over enters the tideway from over Teddington. So that's a shed load, obviously.
Huge amount.
Yes. What was interesting from the estuary process work done, which kind of helped to form the T2100 plan, we had to think about the kind of sediment balance. So the balance of inputs of sediment and how much is there and what's happening and how much is going out. So because historically there was always a feeling there was a gap in the sediment budget, that there's there must be loads of sediment coming in from the outer estuary and supplying it. And they had people thinking, like, because they used to in days of yore when they would dredge out sewage sludge and they'll take out and dump it out in Black Deep, I think, somewhere out there. And they would imagine that it would then be coming straight back in again, chasing the dredger as it came in. So obviously we don't do sewage sludge dumping anymore in the sea, which is always a good thing. But what we found with the kind of sediment budget analysis, that broadly over a longer period, the kind of the budget kind of balances, and not in the kind of grand scheme of things, there's not that much mud gets out. It on a particular year or a particular run of years, it might be different. But if you look in 20, 30-year timescale and take account of the fact that overall the intertidals are at the moment accreting, if you consider from call it Shellhaven upwards, from there upwards, it's all accreting overall. Not to disrespect areas which are eroding. There are areas that are doing that too, but overall, it's accumulating sediment, and that seems to account for most of most of the supplies that come from various places.
What are your thoughts around how climate change will affect the Thames?
Well, I guess the first obvious thing is going to change the mean tide level. The mean sea level is going to change, and the mean water level around which the tide moves is going to change. It's going to go up. So I mentioned there's a process of increasing of the amplitude of the tide due to the bed rising. So there's going to be less of that because the bed will be the water will be a little bit deeper, and so you might have a little bit less of that amplification. But on the other hand, because the mean level's gone up, the region that's fully tidal, where the tide can go right down as far as it'd like to, will be further landward. So at the moment, the maximum in tide range is somewhere Blackfriars area, because beyond there, the rising bed level means that the low water can't go as low as it would otherwise want, and you get that kind of tide which is really distorted with a really sharp flood tide rise and a long ebb tide, and that water level, the low water level there, is much more controlled by what flow is coming down the river. So that process will be less so with climate change, because the tide will be able to go to its full depth or its full low water further up. Not a great deal, but that'll be one change. And the other change is that we're expecting changes to the way the river is behaving. So higher peak flows, episodic flood events will be bigger. But on the other hand, we'll have longer periods of less flow. So we'll have that kind of feast and famine. So sometimes there'll be loads of water coming down, indeed more than we have so far. But on the other hand, there'll be other periods where they'll be reduced. So I guess on the periods where there's less water coming over Teddington and other river tributaries, you'd have thought that the kind of salinity, muddiness would go further up the estuary, further in. And you do see, because you do already see that seasonally speaking, of the maximum in muddiness does move with the river flow. So in the winter, it's much further down. It's maybe almost grave densities. But then in the summer, it moves up river, up estuary. And so you went somewhere around Vauxhall and you looked at the riverbed or the foreshore in the summer, you'd probably find it muddier than in the winter, for instance. And you might expect that kind of influence of the muddiness or the saltiness to be slightly further up during those summer periods. Whereas the winter periods, if there's big floods, it might do the opposite thing and push the muddiness further out. So you can see that the whole balance of different processes, and quite what the net effect on kind of the ecology or the morphology and hence the ecology is really quite complicated. And that's why I think partly why the TE100 plan is this method of tracking what's going on and then responding to it. So because we know it's complicated.
Definitely. So on that subject, a big part of what HR Wallingford does is modelling. I mean, what is modelling for those that aren't sure, and what kind of things are you modelling? Presumably tracking changes in Thames movement, and also things like litter movement within the Thames.
Models are literally, could be anything actually. You could say I have a model in my head of how it behaves. I think of it a bit like that. Or you could go to build an Airfix model. Other brands are available of an aeroplane or something. That's the model. So in the hydraulics world, which is kind of where we are, you could build a real bit of the Thames in concrete, and you could push water down, because there is a whole bunch of scaling rules set out by engineers back in the days of through all the history of engineering, right? So there are scaling rules, so you can build models of estuaries. All you need is water and space, which is kind of partly why we are where we are in South Oxfordshire, which is because when they were looking for a place to put the lab, they needed lots of room, because all their models were these big concrete or mortar constructions, and they needed water. So the site has access to the River Thames there, and it also has various boreholes. So the reason we're there is because of the supply of water and space. So you can build an actual model of it, use scaling, and you can therefore predict things. I want to build my jetty here. What's the currents going to be like? So that was how things have been done until, I think, during a lot of the work towards the Maplin Port Airport, they started realizing that you can't make a physical model. That's what I'm talking about, a physical hydraulic model of the whole world. So they did do one of the Outer Thames estuary, and they built a whole building just to hold it. It was extraordinary. In fact, we do still have the building, and if I stand inside that building, I think, my goodness, this was one model. I think that was extraordinary, actually. As computers came along, of course, people started doing computational based modeling. First of all, you might do it just along a line, so say a river flow, where you know the flow here, you know the water level there. You can probably do some equations. There are equations for water flow, apply them in that way, get a bit more computational power. You start thinking about it in 2 dimensions, so in plan. So you have an actual shape that's recognizable as the location. And then next level, okay, I'm now happy with my 2-dimensional representation of area in my model, and I can now maybe go to 3D, 2 dimensions. So I now represent the changing currents in the vertical. So depending on what you're interested in, so if you're interested in a river, there's not much variation across the width. You go for a 1D model. You're interested in area, variation across the width, you get 2D. And if you know you're a place where it's very important 3D, that's what you have to use. And if you're in some cases where you are interested in, say, like waves breaking on a breakwater, or really complicated things, where the physics or the equations force computers to take forever to do the calculations, hey, there's still a place for using physical models. And that's the whole modeling lab is still there looking at all those things. So wave forces on ships, wave forces on this and that. And there's often numerical models are very good at doing that kind of overall situation, but then in the detail, you might then reflect to a physical model.
That's really interesting that it started off like as a literal physical model, and it's kind of evolved to be more computer equations and algorithms, I suppose. I won't ask you about the equations because I'm going to have flashbacks to my oceanography exams and probably pass out.
That's right. It's true. I think when I do, sometimes I do occasional training in kind of coastal processes, and we kind of equations are the elephant in the room. We know that they're there, but we don't really have, and we know what they do, but we don't really have to know the detail of them.
No, thank goodness. Although there might be some people that are, very sad about that.
The world of the internet, there's endless resources out there, people explaining exactly how the different equations of flow work.
There's a lot of very good YouTube videos on that. I can say
YouTube
that.
is a wonder. There's a very good one on Tides as well. I think someone from Pole has done very good. Shows how the moon and the earth are moving around each other.
Oh, brilliant. Okay.
It's a thumbs up from me.
That's a bit of bedtime homework for anybody out there. What sort of ecology have you been modelling? Yeah,
so I mean, one thing we have, having established kind of the physical processes, it gives you a good benchmark or a testing case to put in other things that might be interrelating with the water flow. For instance, fish, for instance. So we've done work on how fish behave, fish moving around and how they take advantage of bits of the flow. So that's kind of a behavioral model, because you have to judge how the fish behaves in response to certain things. Say noise, for instance. So noise avoidance is quite an interesting one, or other things they might avoid, or other things they might use to move around. We did some interesting work with ZSL on finding spawning grounds in the upper Thames, and that was a combination of the quite intense surveying they had done on juvenile or on eggs, finding them, and then from that putting it into a model and saying, well, this is where that probably came from, which is kind of useful. Other things that are in the river, of course, as we all know, lots of issues on litter and bottles and all those sort of things. And again, we're in process of doing some work on the transport of bottles using the same numerical model of the Thames as a basis to put some bottles in and see how they go. Of course, it falls down to the behavior of the bottle. Is it full of water? Is it at the surface? Is the lid on or lid off? So it's quite good that a lot of the data that's been collected has that sort of information, what sort of bottle it is and whether the lid's on. And then things like wind become really quite important if you're at the surface. So that's an interesting area of research. And other areas a bit like that, to think about, having got the hydrodynamics generally sorted, as it were, what then can you use that for? That's an interesting thing. Final other area we can use it for is ships, and boats moving around. So at Wallingford we have a navigation simulator, and that takes the same currents from the numerical model of the estuary and allows, with overlaid on that would be the behavior of a vessel. So it allows people to really drive around a virtual Thames in a boat as it would do in real life.
That's amazing. That's so interesting. Yeah, I mean, that must be a fun bit of kit to play with as well.
It is. I mean, they have a nice time.
John, thank you so much for joining me today. That was so fascinating and just really good to break down sort of the Thames dynamics. So yeah, thanks for being here.
You're welcome.
I think we can all agree that John's knowledge of the Thames was pretty awesome. He was such a great person to speak to. Thank you for listening to this month's episode of Talk of the Thames. I hope you enjoyed it. Until next month, take care.